All right, I can't believe we're here. It's the last section in this stoichiometry unit on percent yield calculations. We've done this in the lab, and we will continue to do this in the lab. Calculating a percent yield lets us look at the accuracy of our results. It's a comparison of how much product you actually collected versus how much product you were supposed to collect. The actual yield is what you actually produced, what you actually collected. If we were doing some kind of a lab where we had a precipitate and we filtered it and dried it on the filter paper, the actual is what's actually on that filter paper. It is determined experimentally through experimental data, and this is through lab measurements. Experimental data, lab measurements. This one's measured. The theoretical yield is what you should have produced. This one is determined through calculation. So when we go through lab data together in class, often we all have the same theoretical yield. This is done through stoichiometry calculations, using theoretical values off the periodic table. If we all started with the same amount of reactant, we should all produce the same amount of product. That doesn't always happen due to lab errors. The actual yield that comes from measured lab data contains error. The error is often in your actual yield. Sometimes people turn in a lab report and in their conclusion they'll say, well, I don't think we did the calculations correctly. Well, then do them correctly. There's no excuse for not doing the calculation correctly. That is something that is in your control. Change the calculation, do it correctly. Error comes from the actual yield. Things that happened in the lab that caused your final yield to not be correct. And so we kind of looked at this. When you calculate your actual over theoretical times 100, you're usually in one of two categories. I guess you could be in a third if you have 100% yield. Then you're perfect. You're a perfect, flawless human being, at least in this lab you were. That means that you actually collected 100% of what you should have collected. If not 100, maybe you're a little bit under 100% yield. Means that somehow you lost mass. So my actual was less than my theoretical. Maybe we spilled some of our precipitate. We didn't get it all in the filter paper. Maybe we didn't wash out our beaker or our stirring rod. Maybe we spilled some of the precipitate on the table. Something along those lines, that you just didn't collect everything that you should have. Your other option then is to be over 100% yield, which can happen. It means that you gained mass. Now, often it's from some kind of a contaminant. In a precipitate lab, we got to make sure that your final product is dry. If the precipitate's not dry, there's extra moisture or water that's adding mass. So that final mass isn't just your desired product, it's also got water in there. If you used a dirty beaker or stirring rod or something like that, that could add mass so that your final percent yield is over 100. So this has a lot of ties to lab data, looking at the accuracy of our results. If we want to do a calculation, it might look something like this. All right. In the commercial production of the element arsenic, arsenic 3 oxide is heated with carbon. elemental arsenic is formed along with carbon dioxide gas. Fabulous. Okay, so they actually give me the balanced equation. That's nice. When 8.87 grams of arsenic 3 oxide are reacted with excess carbon, according to the equation below, 5.33 grams of arsenic were collected. What is the percent yield? Ooh, there are some things that I like about this. Okay, so number one, here's the equation that I'm eventually going for. Percent yield is actual over theoretical times 100. Cool. So the actual comes from data, which is often in the lab. In this case, we're not the ones doing the experiment, so they're telling us 5.33 grams of arsenic were collected. That's the actual yield. $5.33 grams, that's going to be our actual yield. If we're not the ones conducting the experiment, then somebody's got to tell us the actual yield. The theoretical needs to be determined through calculation. So we're all going to have the same theoretical yield. Now there's something else that I like. This arsenic oxide was reacted with excess carbon, which is just a way of telling us that carbon is the excess reactant. So the arsenic oxide must have been the limiting reactant. So I don't have to calculate the limiting reactant, they're just going to tell me. And so I know right away that it's the arsenic oxide that can be used to determine the amount of arsenic produced. Well, that's kind of nice. I don't have to do the limiting excess deal. It kind of told me excess carbon. All right, so all we have to do is a little stoichiometry. We're going to start with the 8.87 grams of arsenic oxide. And eventually I want to get over to the arsenic, but that's not going to happen in grams. So we got to cancel grams and switch it to moles of arsenic oxide. Cool. Okay, so let's plug this in a calculator. 2 times the arsenic plus 3 times the oxygen. 1 mole. Woo. 196.04 grams. If you like to cross off your units, grams and grams are out. I like that. Cool. Okay, so now that I'm in moles, I can make my switch. I want to get out of moles, arsenic oxide, and over to moles of arsenic. AS, not AR. AR would be argon. That reminds me, a long time ago, the AP kids made a t-shirt that said something about like, kiss my arsenic sulfide. It just said arsenic sulfide. Pretty clever, huh? Maybe just a chemistry geek would appreciate that for its humor. All right, anyways, 42, huh? 42. Arsenic oxide, you are gone. So now I'm in moles of arsenic, which, by the way, you can do this percent yield in either grams or moles, as long as both units are the same. In this case, since my actual yield was given in grams, I might as well just take this from moles of arsenic to grams of arsenic. In some way, they both need to be the same. But if by chance you had both actual and theoretical just in moles, totally fine. You could do percent yield in moles. I'm going to take this one further. Cancel moles of arsenic and switch it back to grams. 1 mole has mass on the periodic table, 74.92. Awesome. So this was just a big mass-to-mass stoichiometry. The original was in grams. I needed to get it out of grams so I could use the ratio in the balanced equation. Then I brought that arsenic from moles back to grams. And if I plug this in, okay, 8.87 divided by 196.04, just going to say times 2 times 74.92, 6.78 grams of arsenic. That's the theoretical yield. Boom, it's this. 6.78. What you just calculated, that's your theoretical yield. Now I plug that in, 5.33 divided by 6.78 times 100 with about 3 sig figs. 78.6%. Cool. So it's really nothing crazy. This percent yield stuff is usually just one extra step at the end of a stoichiometry calculation. They have to tell you the actual if this is being done on paper. If it's in the lab, this just comes from our lab measurements. The calculations will always give us the theoretical. Cool. Okay, so they might ask me what is the percent yield, or they could ask me to spin it a little bit, kind of like these last two. Okay, so part B. Knowing the typical percent yield for this reaction calculated above, if a chemist wanted to actually collect 8 grams of arsenic, how many grams of arsenic should they plan on forming? Oh, brother. Okay, this is all about the wording. I mean, we get the equation, actual over theoretical. Knowing the typical percent yield for this reaction is what you calculated above, 78.6%. A chemist wanted to actually collect 8 grams. That's the actual. How many grams of arsenic should they plan on forming? The amount that should be formed. That's the theoretical. Okay, so we're going to take the percent yield, but this time we can use it as a decimal. 0.786. I actually need 8 grams. We want to know how much should we plan on forming. That's the theoretical. Okay, so be careful when you do this calculation. It's kind of like an equality in a way, like a proportion. You could think of this as 0.786 over 1 equals 8 over x, the theoretical. So I'm going to cross multiply. I'm going to cross multiply these guys. And then set that equal to 8. So in my math, it's going to look kind of like 0.786 times the theoretical equals 8. And now I'm going to divide both sides by the 0.786, and that'll give me the theoretical. The theoretical is 10.2. Okay, so here's what this means. A 78% yield means that you lost about what, like 22%? We're going to lose some. We're going to lose a little more than like 20% of our product, typical for this reaction. Which means then that if you need 8 grams, a chemist needs 8 grams of arsenic on their boss's desk by Friday morning. Well, you got to know the typical percent yield. reactions don't run perfectly. In the real world, we always lose a little product, or maybe you've got some sources of contamination that make your percent yield higher than what it should be. So we need to overcompensate. In this case, I need 8 grams, but I have to take into consideration that I'm going to lose a little more than 20% of that. So we need to plan on forming about 20% extra. So if we plan for 10 grams, knowing that I'm going to lose about 20% of that, I would actually be left with 8 grams. That's what they have to do in the real world all the time. We have to overcompensate for any loss that's expected. And they run these reactions millions and millions of times so that they kind of know a typical percent yield. If we typically lose like 22% of our product, 21.4% of our product, we need to overcompensate for that loss. We're going to plan for 10, hoping to really collect 8. That's what I need. Interesting. Okay, part C, another twist. If the efficiency of this reaction were improved to consistently give an 85% yield, how many grams of arsenic should be collected? 8.87 grams of arsenic 3 oxide react with excess carbon. Well, that's exactly what we had up here in part A when we did our calculations. So this time we have a new yield, a better yield. 85%. I'm going to say 0.85 equals, this time we're going to solve for the actual yield. How many grams should you plan on collecting if this reaction now runs at an 85% yield? Well, it's the same theoretical. It's the same reaction. 6.78 grams was our theoretical. And so same thing, we're going to cross multiply. But that's about it. So basically, we're just saying that, well, if we collect 85% of our product, 0.85 times 6.78 is a big fat 5.76 grams. That's our actual in this case. Oh, we'd only collect about 85% of our product, so just multiply by 0.85. So parts B and C were just little different spins on that equation. Percent yield equals actual over theoretical.